So, as a quick summary, we have polar coordinates and we can measure coordinates in terms of r and theta. And one of the things that bugs me is, we label the points r comma theta, but whenever we talk about polar functions, r is a function of theta. So we're actually like putting the dependent variable first and then the independent variable, which is annoying to me. Like if I had to do it all over again, it would be theta comma r, and that actually makes a lot more sense to me, even in terms of like thinking about where you are. How much are you going to spin? How many steps to take? When you list it as r theta, it's like take this many steps after you spin that many degrees. So had I do it all over again, I'd make it theta comma r. So instead of making it theta comma r, we can also think about x comma y, and here we go. The keys to converting. There's my summary. All right. So polar, because the origin is the pole, and as you may recall, there are some things that are so much easier in polar form. Conics are so much easier in polar form. If you remember the polar form of conics, they all had like the same template, which was like 1 plus a plus be to the something. I forget exactly what it was, but the template was all the same. And it just mattered if you changed a couple of the parameters. It would change it, whether it was like hyperbola. Remember, and you could talk about the eccentricity. Remember, like that, yeah. Right? And actually, if you take like an ellipse and you want to tilt it, it's really easy in polar form. In Cartesian form, it's really, really hard. So there's some things that are just so much easier in polar form, and so that's what I wanted to do next. I wanted to show you, like, hey, here's something that would be so much easier. Go ahead.
What is it? It's like a gradient or grade? It's like a measurement of angle, right?
A gradient?
Gradient.
Yeah. I don't know. Are you asking me what the units or when do we measure gradients?
Yeah, what are the units? You know?
I have no idea.
It keeps on prompting me. Grad. I'm assuming that's.
I think it's
gradients. I've
gradients.
heard of that.
I think that's what it is. And it might be, all right, here's my guess. It might be the y over the x, like the slope, and if you tell it the slope, the gradient, it'll tell you what angle has that, like makes that slope with the x-axis. Could be totally off on that. Just a guess. All right, so I'm going to take this circle, and with a circle of like radius r, you know that the area would be pi r squared, right? Say yes.
Yes.
Yeah. Okay.
Yes.
So one of the things that we've done in calculus is actually.
Oh, I see. Like if it had a radius of 2, it would be a lot easier to do it that way.
Maybe. I don't know.
Because otherwise you get all these square roots of these things. If it's like at a 45-degree angle, let's say. Sorry,
hang with me for a second. So I've been telling you all about like these rectangles and how adding up rectangles is a great way of finding area, right? And in this case, actually, like we would add up the area probably from like 0 to whatever this is. What's that, r? And it would be the integral, and the integral would be like what? The square root of r squared minus x squared, like dx.
Times 4. Yeah.
Times what?
4.
Oh yeah, times 4. Yeah, times 4. There'd be some 4 out here, right? I would actually put forth that integral is not an easy integral to differentiate.
Yes.
Like, there's no chain. Like, it's not an easy one. I don't even know if it's a possible one.
Yeah.
My guess is it is because we can get a number, but I don't know if it's just numerical or not. I'd actually be interested. Can you see if you're...
Well, r is just a constant.
R is a constant, so you could put in like 25. Do you mind seeing if what it would spit out? Because we went from 0 to 4.
Oh,
okay.
Yeah. Okay. Cool.
And you have a...
You can
okay.
You can just go 0 to any number, square root of that number squared minus.
I just want to specify.
Okay. So actually, what I want to start convincing you is maybe not this year, but in years to come, rectangles aren't the end-all be-all. Yes or no? Doesn't like it?
No, you can do like circles from the...
It's pretty long.
Okay.
It's not horrible.
So,
But
hold on. one of the things you could do is you could add up little squares that had a width of dx and a height of dy. And if you had a good way of measuring dx's and dy's, you could actually integrate first with respect to x and second with respect to y. And that's what multivariable calculus does. Multivariable calculus says, hey, we're going to differentiate with respect to two variables. You could also do that. Michelle's saying, hey, we could take
polar form.
we could take rings and add up the rings. Absolutely. And so I want to just reinforce that, hey, rectangles are great and all, but they're only one way that we can add things up, and that's why I want to talk polar.
In order to get rings, you would need everything that you would need to get the full circle.
Okay,
So that,
all right. But so, let's also agree that if someone asks you for the area of a circle, you're going to say pi r squared. Okay, you are not going to integrate using polar form, but I want to show you why it makes things so much easier, sometimes changing perspective. All right, so may have been better served just by redrawing the whole thing.
That's great.
Okay, so instead of doing these rectangles, I'm going to take this little pie slice. Okay. Now, this pie slice has a measure of an angle in here, and I'm going to call that angle d theta. It's going to be a really, really, really small angle. And this is r, and this is r. And I need to figure out what that is.
Are we trying to find circumference or area?
I want to find the area. I'm going to add up all my slices to find the area.
Do you need that side though?
I would love it.
Oh, we know how to get that.
But
like
couldn't you
S
do it
over
without it?
I want to do it with it.
Okay. No. It's not. Like a
Don't you do it the angle in radians times?
So this is arc length, which is r theta, or in this case, r d theta. Now, I also want to take advantage of saying, hey, if you remember from geometry, you would have said, hey, it's like the angle, theta over 360 times the circumference, right? But really what you were doing is if you rearrange that, it's 2 pi over 360 times r. You're taking the angle, and what does this do?
Changing it into radians.
Changes it to radians. So that's what you're doing when you did arc length. You were doing angle in radians times the radius. We would have freaked you out, I think, in 9th grade if we told you about radians being about 57.1 degrees. You'd be like, why would anyone measure an angle like that? So, as theta gets really small, that becomes like a triangle.
Or we can pull like a line almost.
Right? So it becomes a triangle whose height is pretty much r, and whose base is pretty much r d theta. This theta's really smart. Yeah, right?
So it'd be like
So 1/2 base times height. And you don't have to write any of this down. If you want to, you can. But I'm more concerned that you're just like, oh, I see why someone might like to look at things through a polar perspective as opposed to a XY perspective. In this case, theta is the variable, and theta goes from 0 all the way around the circle. So in radians, 0 to in radians.
Oh, sorry.
All right, so 0 to 2 pi, 1/2 r squared d theta. What's my variable?
dr? No, it's theta. D theta?
I'm integrating with respect to theta, so
It's the
theta
radius.
is the variable. What is the radius?
It's just a number.
It's a number. It's a constant. All right. So what's the antiderivative of a constant d theta?
1/2 r squared theta.
1/2 r squared. Whoops, that's supposed to be a square. Don't know what I was doing there. 1/2 r squared theta between 0 and 2 pi. Plug in 2 pi for theta, right? You get pi r squared minus 0 So it's not a surprise.
Wait, but all the way around. Yeah.
So here's the thing. The easy part of what we just did was the calculus. That actually was so much easier than trying to do this. The hard part was getting you to see, hey, we could do this in polar form, right? And when you do it in polar form, it's just a matter of changing perspective. And if you change perspective, you can make some problems very simple in terms of the calculus. So let's look at trade-off. So I'm going to pause there. We can do questions, comments, concerns, and then maybe we'll go back and do either, I want to do a little bit more like with the maybe a little more calculus stuff. So I want to do a little bit more, but there's that for now. Stretch your question.
Well, the integration for that actually is not too terrible.
Oh, for this one?
Yeah.
All right.
Basically, what
Does
you
it
do
simplify out?
is no.
Oh, all right.
You just pull out a square root of 5 squared or whatever, and you end up. It's long, but it's not really that complicated. It's 25 arc sine of x over 5 divided by 2 plus x square root of 25 minus x squared
Yeah,
over
that
2.
seems simple.
So wait, so hold on.
Is
So
because it's just a bunch of like very.
so is it
straightforward
maybe
identities.
maybe, and I'm totally going out on a limb here. Maybe it's an integration by parts where you're trying to get an arc sine involved or something.
I thought of it as like the square root, and then you multiply it out, so you're gonna get square root of 1 minus x squared over 5 squared, right? And then you can. That's gonna come out. The x squared is gonna be x over 5, and then you could. That's the formula for arcs of arc sine.
So we are all right. So we're trying to get an arc
Derivative
sine.
yeah.
Okay. All right. So I will concede, not impossible. I will say
No,
this
definitely
more
easier.
straightforward, right?
Need
Sophie,
a calculus.
Over here, why didn't we integrate that?
we did integrate. What's the variable?
Theta.
Theta. So if you're integrating a constant times theta,
Oh,
the
okay.
antiderivative
Okay.
is constant theta. Is that okay?
Yeah.
Wait, plus c.
Definite integral, don't need to worry about the plus c. You can write the plus c, but you're just going to do plus c minus c, and in this case it will be the same c, and they'll drop out. Is that okay? Trying to think if there's anything more from pre-calc that I will remind you of. I don't know that there is. Well, maybe we'll get a calculator. So I will say, like, you might remember, like, hold on. You might remember thinking, like, I think you were playing around with like a bunch of.
This is how you make a flower. Is using
Right.
polygons.
So you can make flowers. I think this is the cardioid graph. I'm not
Oh, we're gonna
positive.
have to memorize these all together? No.
No, you don't have to memorize them.
Yeah.
So
I was like,
zoom.
actually, it's cardioid. It's like
There's a lemniscent, right? So like
lemniscate.
lemniscate. Sorry. So the cardioid has this little bump that looks like a heart, right? The lemniscate.
I'm not sure actually.
Like
if that's
I think is that the one that has the belly button in it,
Yeah.
the curve in it.
Can tell.
Okay. So here's my R, and I want to show you when you go to your window, very similar to when you were in parametric mode, right? You have to tell like what sort of values of theta do you want to plug in. Now I'm in radian mode, so I'm going from 0 to 2 pi, and a theta step of around 0.1 is good. If you use something that's like 2 or 5, it'll be really chunky. You wanted something like 0.1. If you do like 0.01, it'll just take forever to plot. And so, sorry.
Is the new version of this calculator like super fast and plotting?
I don't know.
It looks the same.
But is it?
Look any different.
I feel like this
I
is
don't
like
know.
the amount of time it takes to graph is like it's probably its biggest flaw.
Oh, you just don't. This generation. So wait,
But I know my
do
dad.
you remember? Like, didn't you when you first did polars? Didn't you plot these by hand when you first started out?
Yeah.
Didn't you get polar graph paper and you're here like,
Oh yeah.
yeah, right? Okay,
No,
yeah,
because
that's what I'm looking
No, he
for.
got-
Yeah.
It was really, really
Who wants
low
to do
quality
that?
polygraph
Oh,
paper.
yeah, it's terrible, right?
I mean, it's obviously way
All right,
faster than you can.
So if you go to second calc, I want to show you that you can calculate the value based on r. You can also calculate dy over dx, the derivative of y with respect to x, for a given, sorry, not for r, for a given theta value, or you can calculate dr or d theta. Now I want you to understand though, dr d theta is how much the radius is moving with respect to how much the angle is moving.
Yeah.
So like when you say dr d theta equals 0, you don't mean that there's like a horizontal tangent line. You mean
It's a
the
circle.
r isn't changing, right? And if dr d theta was always 0, you get a circle, right? Absolutely.
Wait, I have
Right.
a question. When you set your window, and you did it from like 0 to 2 pi,
So
like could
not
you,
so my theta, the values that you're going to pick to make your table, you're picking theta values between 0 and 2 pi.
like if you say that, I just don't know what the value would be in radians, but say it was like in degrees, could you do like 5 to 365, and that would be the full graph?
Yeah.
Or like,
Well, so if
how would you?
you're-
If
so you're
you're
asking-
starting not at 0.
Yeah.
What would you go?
so we could go, hey, let theta min be pi and let theta max be 3 pi, right? So watch the graph now when it graphs. It just starts at a different spot, but it will complete it. Because for this graph, the period is 2 pi. Because it's 3 plus 2 sine theta, the period's 2 pi. If this was sine of 3 theta, it'd be a different period, right? And so my theta min and max could be different. And if your theta min or max is more, it just retraces itself, right? It traces over itself again.
And if it's less, then would you have a cutout?
Yeah, you'd only have part of the graph.
Oh.
So it wouldn't be a cutout so much as it would just
Yeah.
like, it would be continuous, but you wouldn't have the full thing.
Mhm.
Okay. All right, so let me talk to you a little about slope. So here's what I want to remind you. I want to remind you that x is r cosine theta, and y is r sine of theta. So in essence, x and y are parametric
With respect to theta.
with respect to theta and r, because r is a function. So this is actually sort of interesting. This is a little new. We have these two functions are parametric with respect to two functions. Theta, which is a variable, and r, which is a function in terms of theta. So I want to talk to you about the derivative, and then maybe we'll do a practice problem. So if I want to calculate the derivative, dy, well, that's the derivative of r sine theta. But remember, r is a function, theta is a variable.
We
So,
have to chain on, like with implicit differentiation.
all right, so implicit differentiation, and what's the rule?
You have to chain on the derivative of all.
Product rule. So product rule with the chain in mind. Okay, so first times the derivative of the second plus the second times the derivative of the first, which I'm going to say dr d theta, dr over d theta, because r is a function of theta.
Oh, and that's why you don't have to do like D for the other thing.
Theta's the variable, so I don't have to chain on d theta. I
Yeah.
could, it would just be one. So just to like make the parallel, like right here's the function, and there's its derivative. Understanding theta is a variable and r is a function.
Wait, shouldn't it be?
Did I mess up?
Oh, yeah. No, I got it.
Wait, and so
I
if,
might be off by a minus. Am I right? Or did I take my derivatives right? Okay.
if they gave you a value for r, though, you wouldn't. Well, yeah. See, that's the thing. If they gave you a value for r, then r wouldn't be a function anymore. So wouldn't it just be
No, r is a
No, it'd still
function.
be a function.
Like
radius? Or like if they gave you a value for
I
like
mean, if they
radius.
give you like the radius was 5.
Like yeah, they say like radius.
R
is
equals
5.
1?
Yeah.
yeah,
It's still.
that means no matter what theta is, the radius is 1. R is a function of theta.
So then
So
I
the
guess you would just plug it in.
right.
Yeah.
But now what happens when we do the dr d theta?
Zero.
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 So that term goes, right? So we would get r 1 times cosine theta over, we didn't do the over x. All right, so first
Negative R.
times the derivative of the second. So that's where the negative comes from?
Yeah, negative.
All right. Plus the second times the derivative of the first. And just to make sure we're understanding, that goes with that. So it's not that they're equal, but one's the blue is the derivative of the blue, the yellow is the derivative of the yellow. Noticing that there is a chain, right? So, can we try a problem, or do you want to ask a question?
Wait, do we have
Do you have to be given like an R equation
So-
or
Yeah, so this works if I say, hey, here's a... Get out your classwork.
If we did the double derivative, would it be the same as before, where you do like
Um,
derivative of that over the bottom?
I don't know. I'm just being upfront on it. So I haven't done concavity of polar functions. I don't know. All right, so let's see. Oh,
I get through time.
all right. What are we doing? Tell me. All right, so like 9 through 12 are like pre-calc kind of problems. So 13A. 13A is a good problem to take a look at. Can I give you like a minute or so to work on it, or do you want to do it together? Don't really care.
Can we do it together?
Yeah.
Absolutely. Okay. So the function in this case was what? R
Equals sine.
equals sine of theta, and we're trying to find where there are horizontal and vertical tangent lines. All right, fine. Horizontal tangents are when
dx or d whatever dy equals 0.
right. So if the vertical is not changing, right? If that's 0, that's where we have a horizontal line. So if we're not changing in the vertical direction, if the dy piece is 0, so I'm really looking at that numerator, right? So when is dy over dx equal to 0? Precisely when, help me out, r sine theta plus cosine theta dr over d theta, right?
Wait. Oh, because
that-
that's the thing we just derived.
Is that-
basically.
Am I right?
Yeah.
Oh, it's also
No, isn't it
Nope.
r
Yeah.
cosine theta? Oh, is it backwards?
Oh, because that's all, you always can just use what y equals and what x equals, not dependent on what your function is.
Am I right now?
Yeah.
Yeah.
Skip 5.
Well, hold on. For finding out when it's equal to 0, you're right. The denominator is not really important. All I really need to worry about is the numerator. Do I know what r is? Yeah. Do I know what dr d theta is?
Yeah.
What is
Negative
dr?
or cosine theta.
Yeah, go ahead, Dan.
I'm confused as to how you got that whole thing from just R equals sine.
I know what the derivative is. I memorized this.
Oh, so it's just the same thing from.
Yeah, we just said, hey, the derivative is equal to, like, for any function, any polar function, the derivative dy dx is equal to r cosine theta plus sine theta dr over d theta.
Okay, that makes
Okay.
sense.
No, sorry if I made the
Yeah, no.
jump without taking people with me. All right, so I know what dr d theta is. I know what I know what r is. So basically I'm asking the question, hey, when is
Why does, oh,
sine theta cosine theta plus sine theta cosine theta equal to 0?
It's a double angle.
So 2 sine theta cosine theta equals 0. I have a choice. I can change that to sine of 2 theta. So I can either ask the set
Can
question.
you divide everything by 2?
Yeah, or I have a product here that equals 0. If the product equals 0, what has to be true about the factors?
Either sine of theta equals 0.
Or cosine of theta equals 0. So either way, when is sine of theta equal to 0?
0.
All right, so when theta is 0,
Theta's pi over 2.
Pi d.
Or pi.
pi. When's cosine equal to 0?
Pi over 2.
Pi over 2.
But that's not on. It would be 3 pi over 2, but that's not on the interval. It's only
Yeah, because
from
they
0
just
to
want
pi.
it from 0 to pi.
Just 0 to pi?
Yeah.
All right, fine. So I don't have to worry about that. Now, I might be interested in going to graph, right? So if I actually graph that, oh gosh, sorry. If I actually graph that and let's see. I'll graph it. Maybe I'll have to adjust my window. Yeah, that's pretty small, right? So maybe I'll do like window. Oh, all right. So horizontal tangent line here, horizontal tangent line there. If you calculated the theta value, you'd probably find that that was at 0, pi over 2, and pi.
But what do they want when they ask you for the line? They ask you for
When they ask you for what?
when it says find the horizontal and vertical tangents of the following polar functions. So if you found theta, then you need to find r or no.
Well, so I mean, if you wanted to, you could say y equals 1, y equals 0. Sorry, yeah, y equals 1, y equals 0. You could say when theta equals pi over 2,
That's
you get a
fine.
horizontal
That would be fine.
tangent line.
Okay.
All right, sorry for going a little late. Get out of here. Have a great day. Be good and kind. Stay out of trouble.
Mr. Gregorian, why are you so cold?
Because we're doing polar coordinates.
That is a weird.
That was my own part. That was really sad.
I didn't realize that we were in that